Right, in this video we're going to take a look at the proof of the sum of a geometric series formula, and it's one of our proof by inductions. It's very straightforward. The problem with it is sometimes they might present the question like this: just prove the SN formula. And what you'll need to do first for yourself is actually to write out the series and what it's going to be equal to. So that's really going to be transformative and allow you to kind of better answer the question, and the proof will become a lot easier. So the first part of a geometric series, remember the first term is just called A. What's happening in a geometric sequence is that each time it's being multiplied by R. So the next one will be AR. Now what we're talking about here is the sum of all of them. So we're not just going to say A comma AR, we're going to say A plus AR. The next one, each time what you're doing is you're multiplying it by R. So it's going to be A by AR, and then the next one's AR squared, then the next one will be AR cubed, and we're going to keep going, and that pattern will continue until I get up to the end. Now the end is going to be A times R, and it'll be n to the power of n minus 1. So that's really important. That's a place where I would make a mistake often. I would forget that the last one is not AR to the n, but AR to the n minus 1. And the way that you can kind of catch it is that if the first term is A, then that had to be R to the power of 0, right? And the only way that you would get that if n is equal to 1, that the power is equal to 0, is if it's n minus 1. So just remember that the last one is A to the R n minus 1, and you know that then has to equal to this. This is what we're trying to prove. And you don't have to do this, but personally for me, I find it much easier to do the proof out if I start with that written out. The next thing then is I'm going to start my proof. So the first thing is prove true for n is equal to 1. And then remember, because you've said prove, you cannot set them equal to each other. You have to do LHS, RHS, left hand side, right hand side. So what is my first term? Well, if each term is generated by this formula, AR to the n, which is now 1 minus 1, what I'm going to have is AR to the 0. So the left hand side works out to be A. What does the right hand side work out to be? Well, I'm going to have A by 1 minus R to the 1 all over 1 minus R. Well, what do I have then? I've got A by 1 minus R all divided by 1 minus R, and then I have doing and undoing. So they're gone. So that's also A. So then I have LHS equals RHS, and then you say therefore true for n is equal to 1. Okay, that was nice and straightforward for the first one. The next one is you're going to assume. So the word that I got you to remember this by is PAP. So it goes prove, assume, prove. So we're going to go assume true for n is equal to k. Now, because it's an assumption, you are allowed to let them equal to each other. So I'm going to cheat a second here, and I'm going to just take this down, and I'm going to replace the letter n here with k. But that's what you would do, is you'd write it out again, but you would, instead of writing the letter n in those positions, you're going to write the letter k, like so. So the next thing that you're going to do is you're going to do prove. Okay, so you're done. That's it. You've got 50% of the marks in the bag. So you're going to go prove true for n is equal to k plus 1. So now we're going to go through the proof again. And because you've said proof, you can't let them equal to each other. You have to say LHS and you have to say RHS. I'm going to leave a little bit of space on the left hand side this time, so we have a bit of work to do. So what I'm trying to do this time is show that this, now it's not just this, I'm adding on to it the next one in the sequence, which would be, if I've got k minus 1 as the last one, the next one in the sequence. That's all that the k plus 1 references, is the next term in the sequence. So I'm going to have AR to the power of k. And the right hand side then is straightforward enough. It's just A and then 1 minus R to the k plus 1 on the top, and then 1 minus R on the bottom. Now, The next thing, as soon as I do this next step, you'll know, because I told you loads of times, that if you do this next part, you're on 70%. So I'm going to take all of this piece here, and I'm going to say that that was assumed to be equal to this in step 2. So this here, and then I'm going to say it's replaced with a by 1 minus r to the k all over 1 minus r. And if you wanted to put in a little line about how it was assumed in step 2, you can do that. But as soon as you've brought it in to the proof part, you've got your 70%. Okay, so you've made an effort to do the proof part. The next little piece is just algebra. So what do I need to do then to get to have these as one fraction? Because that's what I have on the right hand side here is one fraction. Well, to do that, I'm going to multiply this top and bottom by 1 minus r. So then I'm going to have a r to the k by 1 minus r all over 1 minus r. So that's just an algebra skill. Nothing new there. And then we're going to have a 1 minus r to the k all over 1 minus r. Now they're the same denominator, so I'm going to just put them over the same thing. And then, see the way a is in common to both, so I'm actually just going to factorize that out of kind of a big bracket. Then I would be left with 1 minus r to the k plus r to the k into 1 minus r. What I can do now is I can try and tidy up the brackets a little bit. So I'm going to have a into 1 minus r to the k plus this by this is r to the k. Then this by this will be minus r to the k. And then when you've got indices with the same base and you multiply them, you add the powers. So I'm going to say plus 1 up the top there. And then on the bottom, we're going to have 1 minus r. All right, so there we have that. I'm going to tidy up the bracket now and look what happens. This and this, it's doing and undoing, and then I'm left with a into 1 minus r k plus 1, and on the bottom I'm going to have 1 minus r, and then hopefully you're able to recognize that. That is the same as what we have on the right hand side. So now I'm going to say left hand side equals right hand side. Therefore true for n is equal to k plus 1, assuming true for n is equal to k, or based on the assumption that it's true for n is equal to k. Since it is true, since true for n is equal to 1, it is true for n is equal to 2, 3, 4, da 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 da, and all values of n that are natural numbers from what we've proven. So there you go. Don't forget that little sentence at the end. You'll lose a mark if you don't kind of round it off nicely for yourself. So you're saying, I've just proven it true for k plus 1, given that, or assuming that it's true for k, and this then has the knock-on effect because I know it's true for 1. If it's true for 1, then it's true for 1 plus 1, and then 2 plus 1, and then so on and so forth. So that's your proof of the sum of the geometric series. A really nice one if it does get asked, because it's really systematic. Just remember your headings, and then remember once you get to this step and you've substituted out part of it for the assumption step, 70% in the bag. And if you want to jump ship at that point, you've got loads of marks in the bag. The last little part is really just about the algebra.